In this video, we are going to go through example number 4, which focus more on the relation between the motor speed and the motor torque. Actually, when we study the characteristic of the induction motors, we see the induction motor can operate, or the induction machine can operate in two different regions actually. uh, if the speed of the induction motor is less than the synchronous speed, as we can see on the left side of this graph, so the induction machine will operate as a motor. But if the speed of the machine is increased more than the synchronous speed by using prime mover here, so the machine will act as a generator. So instead of taking electrical power give mechanical, it will take mechanical power from the prime mover and it will give the output as electrical power, so it's become as a generator. So here you can see it's operate as a generator and here it's operate as a motor. Okay, so the characteristic of the torque is with relation to the speed. You can see here that starting torque is a little bit high, which is usually 2 times as the rated torque of the machine or of the motor. Then it's go linearly with the increasing of the speed. So the torque increase with increasing the speed until it reach to the pull out torque, which is the maximum value of the torque, which is sometimes 2 to 3 times double of the rated torque. Okay, then near to the synchronous speed, to the torque will goes down, and at the synchronous speed, the value of the torque which goes to zero, then it goes to the negative values. Okay, so in this example here, we have the value, we have the two ball. That means the value of or the number of poles is 2. 50 hertz induction motor supplies 15 kilowatt to the load supply. So this will be the power for to the load. Okay, and here is will be the machine speed or the motor speed. Okay, what is the motor slip here? He asked for about the value of S, and S equal to usually NS minus NM over NS. So we need to calculate the value of synchronous speed. From the synchronous speed, we deduct the value of the machine speed, which is NM here. This represent NM, or the machine or the motor speed. Then we can find the value of S. So as we can see here, NS equal to 120 F over P. So which equal to 120 times 50 hertz in this case over P, which equal to 2 volt. So it will give you the synchronous speed, which is 3000 RPM. Okay, so from synchronous speed here, we just substitute NS here, which is 3000. So it's become the value of S here will equal to 3000 minus the value of Nm, which is 2950 over 3000. Okay, so it gives you the value of S, which is equal to 0.0167 or 16.7%. Okay, this is the first question of this example. The second part, what is the induced torque in the motor in Newton meter under these conditions? So we want to find the value of tau induced. So the tau induced, actually, we said the the value of tau usually equal to P over omega. Okay, the general formula of the torque is T or tau equal to P over omega. We said the value of P, value of omega, depends on where we are going to calculate the torque. Is it the torque which move from the stator to the rotor, or is it the output torque of our motor? So in this part, since there is no fractional loss mentioned in the example here, because he didn't mention for any fractional loss in the example, he just go directly to the power or to the output power. So we are going to assume that the P converted is equal to the P load. So all the power which convert from the stator will go to feed the load. So the induced torque here will totally depends on the value of the output power. So the output power is 15 kilowatts. So that we are going to substitute for the value of power here. Torque will, or induced torque will equal to 15 kilowatt or 15,000 watt over omega. Omega here is the speed of the machine, which is or the angular speed of the machine, which come from the formula 2 pi over 60 times omega m, or times nm, which is 2950. So in this case, we can find the value of tau induced or induced torque, which equal to 48.6 Newton meter. As you can see here in the slide. So this is the induced torque here. Because we said the frictional loss and windage loss or the mechanical loss are not given or ignored in the question, we assume that the B converted is equal to the P load and tau induced equal to tau output or tau load. So tau induced here, B converted over omega m, B converted actually is equal to the P load or the P output, which is 15 times 10 to the power of 3. We convert it into watt, then we divide it by the speed omega m, or the angular speed of the machine or of the motor, which give you this 48.6. Okay, then the next question here, or the next part of our example, is what will be the operating speed of the motor if its torque is doubled? So the torque, that means the value of this torque that we calculate now, this torque will be doubled, means 48.6 times 2. So in order to find the value of the speed at this point, we should see the relation between the torque and the speed in this area. Actually, in this area, or when the value of sleep is small in this area here, the value of sleep is very small. That means m is too close to the value of ns. The relation between the torque and the sleep, it look like linear relation. So either it will increase with the sleep or decrease with the sleep, depends on the relation, the situation of the sleep. Okay, so if the relation is linear, that means if the value of the current, he said here, if the torque is doubled, that means also the value of slip will be doubled. That means s, instead of become point 0.0167, s will be multiplied by 2. So the relation here will be multiplied by 2, because it will the relation between them is a linear relations. So as we can see here, the value of S become 3.33, 1.016 times 2, so it will give you 3.33 percent. Okay, if the value of the slip is doubled, so we need to use this value to calculate the new speed of the machine. So n machine equal to 1 minus s. This s is the new s here, so times the synchronous speed, which is constant at 30,000. Okay, so we can find the value of the new speed, which is 2,900 rpm. So if the speed, if the torque of the motor is doubled, so the value of the machine speed also will be a little bit decreased from the machine speed, which is what it was 2,950. Here it's become 2,900. Okay, the last question here, he said how much power will be supplied by the motor when the torque is doubled. That means in the case of the torque become times 2. So I have, this is the torque 48.6 times 2. So it will become 96 or 97.2. So the new torque here, I have the new torque, which is 2 times 48.6. So I need to find the new power, or the new converted power, or new output power. So the torque is times 2, and the speed omega m is the new speed at the doubled torque, which is 2,900, converted into radians, so multiply by 2 pi over 60. So the value of the converted power in this case become 29.5, while in the first in the beginning the value of the power was 15 15k or 15 kilowatt. Okay, so now become like 29.5 kilowatt. It looks like also the power is doubled also. So this you can refer to this graph actually in your slides, which show you the relation between the torque and the speed, and how the torque is start from a high value, which is roughly 200%, or it's doubled of the started or the rated or the full load torque. Then it's go to the pull out torque. Then it goes down when the speed is near to the synchronous speed. At the synchronous speed, the value of the torque equal to 0. For that, we said the machine must running at speed less than the synchronous speed. Thank you.